Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
Hey everyone, glad to be back. Today's topic is particularly interesting, measuring AI's ability to complete long tasks. It's a huge challenge, really.
Definitely. It's not just about getting a task done, but how it's done and whether the AI actually understands what it's doing. That's what I always think about.
Exactly. And it's not like we can just throw a bunch of data at it and hope it figures things out. There's a deeper level of understanding that's needed, especially with tasks that unfold over time and space.
Right. So, where do we even start with measuring this? What are the current approaches, and what are their limitations?
Well, a lot of current metrics are still focused on simple success rates. Did the AI complete the task? How long did it take? Basic stuff. But that really doesn't tell you much about the AI's actual comprehension or planning abilities.
Exactly. Think about a self-driving car. It might successfully navigate a route, but did it understand why it took that specific route? Could it adapt if there was an unexpected detour or road closure? Probably not, without a lot more data.
And that's where the spatiotemporal aspect comes in. It's not just about the car seeing an obstacle. It's about understanding the obstacle's trajectory relative to the car and planning a maneuver that takes into account the car's own momentum and the surrounding environment. Current AI is still pretty clunky at that.
Mem, it's like the AI is just reacting to individual data points rather than understanding the underlying physics and relationships. It's just doing pattern matching, which can be fragile.
Yes, but I think even with pattern matching, deep learning has made strides. Think about tasks like machine translation or even playing complex games like Go. Those involve long sequences of actions and intricate planning. The AI is learning implicit representations of the rules and strategies.
But is it really learning the rules? Or is it just finding statistical correlations that happen to lead to a win? Because if it's the latter, it's not going to be very robust when faced with novel situations.
I agree with Sarah. I think deep learning is still very brute force. It needs so much data to learn even simple things. A human can learn to ride a bike with like a few hours of practice. An AI would need thousands. And it still wouldn't understand the physics of balance.
And that's where I think we need to look to neuroscience for inspiration. The brain doesn't just process data, it actively constructs models of the world. It's like building a mental simulation that allows us to predict and reason about what's going to happen next.
That's interesting, Jesus. Do you mean we need to start building AI that mimics the brain's hierarchical processing, like how the visual cortex processes information in stages from simple edges to complex objects?
Exactly. Think about how the brain uses working memory to hold information temporarily while it's being processed. That's crucial for long-term tasks that require multiple steps. And then how it encodes that information into long-term memory for later retrieval. We need to incorporate those principles into AI architectures.
But how do you translate those biological principles into something that's actually implementable in AI? Because the brain is incredibly complex and we still don't fully understand how it works.
I think that's where neurosymbolic approaches come in. Combining the strengths of neural networks for pattern recognition with the symbolic reasoning capabilities of traditional AI. It's about building hybrid systems that can both learn from data and reason about the world in a more structured way.
Yes, I'm a big proponent of neurosymbolic approaches. The problem is, how do you effectively integrate those two paradigms? How do you get the neural network to generate symbols that are actually meaningful and useful for reasoning?
And more importantly, how do you represent spatiotemporal relationships in a way that the AI can reason about them? It's not just about recognizing objects, it's about understanding how they move and interact with each other over time. Think about predicting the trajectory of a bouncing ball. That requires understanding physics, geometry, and time.
Right, Donald. So, you're saying the AI needs to be able to translate between different coordinate representations? Like from visual input in pixel space to a more abstract representation of the object's position and velocity?
Exactly. And not just position and velocity, but also things like orientation, angular momentum, and even more abstract concepts like the object's intention. If the object is a person, for example, the AI needs to be able to infer their goals and predict their actions.
Okay, but that sounds incredibly complex. How do you even begin to build an AI that can do all of that?
That's where structured knowledge representation comes in. You need to give the AI a framework for understanding the world, a set of concepts and relationships that it can use to reason about what it's seeing. It's not just learning from scratch.
Like a knowledge graph, maybe, where nodes represent objects and concepts, and edges represent the relationships between them.
Yes, exactly. And then you can use a neural network to learn how to map from raw sensory input to this knowledge graph. That way, the AI isn't just memorizing patterns, it's actually building a model of the world.
So instead of the AI learning to drive by watching millions of hours of video, you would give it a knowledge graph that encodes the rules of the road, the physics of motion, and the goals of driving.
Precisely. And then the neural network would learn how to use that knowledge graph to make decisions about how to drive. It would still need data to fine-tune its parameters, but it wouldn't need to learn everything from scratch.
But how do you ensure that the knowledge graph is complete and accurate? The real world is messy and unpredictable. There are always exceptions to the rules.
That's where the learning aspect comes in. The AI needs to be able to update its knowledge graph as it encounters new information. It needs to be able to learn new concepts, refine existing relationships, and even discover new rules.
So, it's a continuous process of learning and reasoning. The AI is constantly updating its model of the world based on its experiences.
Exactly. And that's what makes it truly intelligent. It's not just a passive observer, it's an active learner.
Okay, but let's get back to the original question. How do we measure all of this? How do we know if the AI is actually building a useful model of the world?
I think we need to move beyond simple success rates and start looking at more nuanced metrics. Things like generalization ability, robustness to noise, and the ability to explain its decisions.
Generalization ability is key. Can the AI perform well on tasks that it hasn't been explicitly trained on? Can it adapt to new environments and situations?
And robustness to noise is crucial. Can the AI still function effectively even when the data is incomplete or corrupted? Can it filter out irrelevant information and focus on what's important?
And the ability to explain its decisions is essential for trust and transparency. We need to be able to understand why the AI made a particular decision so we can identify potential biases or errors.
Imagine an AI that's diagnosing medical conditions. It's not enough for it to just give a diagnosis. It needs to be able to explain why it thinks the patient has that condition, based on the available evidence.
Right. And that explanation needs to be understandable to a human doctor, not just a bunch of technical jargon.
Exactly. And that's where symbolic reasoning comes in. The AI needs to be able to articulate its reasoning in a way that makes sense to humans.
But how do you measure the quality of an explanation? How do you know if it's actually accurate and complete?
That's a tough one. I think we need to develop new metrics that specifically evaluate the quality of explanations. Things like completeness, coherence, and relevance.
Completeness. Does the explanation cover all the relevant factors? Coherence. Does the explanation make sense and follow a logical line of reasoning? And relevance. Does the explanation focus on the most important aspects of the decision?
Yes, those are all important. And we also need to consider the context of the explanation. Who is the audience? What are their goals? The explanation needs to be tailored to the specific situation.
And we need to be careful about anthropomorphizing the AI. We shouldn't expect it to explain its decisions in the same way that a human would. It's a machine, not a person.
Right. The goal isn't to create an AI that can mimic human reasoning perfectly, but to create an AI that can solve problems effectively and explain its solutions in a way that's understandable to humans.
Okay, so we've talked about a lot of different aspects of measuring AI's ability to complete long tasks. What are some concrete examples of how these metrics could be applied in practice?
Well, let's go back to the self-driving car example. Instead of just measuring whether the car reaches its destination, we could also measure its ability to handle unexpected events, like a pedestrian suddenly crossing the street.
Right, a really common example. We could measure how quickly it reacts, how smoothly it brakes, and whether it avoids hitting the pedestrian.
And we could also measure its ability to explain its actions. Why did it brake so suddenly? Why did it swerve to the left instead of the right? The explanation could be based on its perception of the pedestrian's trajectory, the car's own speed and position, and the surrounding environment.
And you could even test it in a simulated environment with different types of pedestrians, different weather conditions, and different road layouts. That way you could get a more comprehensive assessment of its capabilities.
Another example could be in robotics, specifically in manufacturing. Imagine an AI system that's responsible for assembling a complex product, like a smartphone.
Instead of just measuring how many phones it can assemble per hour, you could also measure its ability to handle errors and exceptions. What happens if a part is missing or defective? Can the AI diagnose the problem and find a solution?
And you could also measure its ability to optimize the assembly process. Can it find ways to reduce waste, improve efficiency, and increase the quality of the product?
And again, you could test it in a simulated environment with different types of parts, different assembly procedures, and different quality standards. That way, you could get a more realistic assessment of its capabilities.
Those are great examples. I think the key takeaway here is that we need to move beyond simple, task-specific metrics and start developing more general-purpose metrics that can capture the underlying intelligence of the AI system.
Yes, and we need to focus on measuring things like generalization ability, robustness, and explainability.
And we need to remember that AI is a tool, not a replacement for human intelligence. The goal isn't to create AI that can do everything that humans can do, but to create AI that can augment human capabilities and help us solve complex problems.
Exactly. I still suspect that unlocking coordinate translation is the key to all this. Current brute force methods aren't going to cut it.
So, thinking about future research directions, from my perspective, I'd love to see more work on integrating neurobiological principles into AI architectures. Specifically, how can we model the dynamic interplay between short-term and long-term memory representations in AI systems to improve their ability to maintain context and perform extended computations? Also, how can we integrate neurobiological models of cognition, specifically the role of hierarchical processing and working memory, into the architecture of decision trees?
From my side, I think we need to focus on developing better metrics for evaluating the meaning behind learned representation. If the current approach to long-term task completion in AI relies heavily on brute force data processing, how do we determine if the learned patterns are truly indicative of understanding or just statistical associations? Also, I'm fascinated by the potential for incorporating hierarchical temporal memory, HTM-like structures into deep learning models. It seems like those models might offer a more biologically plausible framework for understanding how the brain performs tasks that involve sequential reasoning and memory.
I'd like to see more research on neurosymbolic methods. How can the strengths of symbolic representation, like clear rules and logic, be combined with the learning capabilities of neural networks in order to better tackle the complexities of long-term tasks? Why are we so fixated on purely data-driven approaches when the fundamental mechanisms of intelligence are so likely deeply rooted in structured knowledge and symbolic reasoning? The limitations of current deep learning models are not just computational, but also conceptual.
I think we need to focus on finding a way to model the nuanced relationship between different coordinate frames in an AI model. It might reveal insights about how spatiotemporal processing occurs in the brain. The concept of coordinate translation in an AI context, akin to how a human brain likely handles spatial and temporal information, feels like a crucial missing piece. It might be the key to unlocking the kind of complex reasoning that goes beyond simple pattern recognition.
Excellent points, everyone. It sounds like there are many exciting avenues for future research in this area. Thanks for the stimulating discussion.
Great to be here. Thanks for having me.
Yes, thank you. Always a pleasure.
Likewise, always enjoy these conversations.